Hi guys, and welcome back to the channel. Today we're going to be deriving the Rydberg's constant, which I talked about in the last video, and how it and its relation to the energy levels in hydrogen atoms and other isoelectronic atoms. So in this video, I'll just be using three main concepts. First will be the concept of centripetal force. The second will be Coulomb's law and the electrostatic attractions. And third, which was the key factor in sort of determining what this Rydberg constant was, is the quantization of angular momentum. And I briefly mentioned that in the last video, but in this video we'll actually be using it to derive what the Rydberg constant actually is. So let's get started. Okay, so in a hydrogen atom, we basically have a nucleus. And I'm going to, in my derivation, I'm going to do any isoelectronic atom or ion. So basically, I'm going to call this nucleus is going to have an arbitrary number of positive charges. So the charge on the nucleus I'm going to call is Z times E, where E is the charge of an electron or the charge of a proton. Z is the number of protons, and this is called our nuclear charge, right? And around this atom, around this nucleus, we have our electron orbiting. And this electron has a charge of negative E because it has a negative charge. And positive charges and negative charges attract. And the law that tells us what the force is of this attraction is Coulomb's law. So the force Coulomb is equal to K, which is the proportionality constant, times the product of the charges divided by the distance squared. So this is really similar to Newton's law of gravitation, if you've seen that, where you have product of the masses divided by distance squared. This is product of the charges divided by distance squared. Now if I plug in the charges, right, I get K times negative E times ZE divided by distance squared. And I'm using this distance if I'm labeling it on the diagram. So this gets me KZ E squared over R squared. This is the magnitude of my force. And the direction of the force is towards the nucleus, right? Basically what centripetal force tells us is if this electron is orbiting around the nucleus, this Coulombic attraction must be equal to the centripetal force. So force Coulomb must be equal to the centripetal. And what is the equation for centripetal force? This you might have seen in an intro physics class, but the equation for centripetal force is the mass of the electron times the velocity of the electron squared divided by the radius, mv squared over r. So basically now we're just going to set these two things equal to each other and do some math from there. So K times Z E squared over R squared equals MEV squared over R. And we're going to extract two different things from this information. First, we're going to solve for V, which is the velocity at which our electron is orbiting the nucleus. So let's solve for V really quickly. If you move some things around, you'll get that V equals the square root of KZ E squared, right, divided by ME times R. Okay, so now we've solved for the velocity of the electron in terms of other constants. And note that K is just a proportionality constant for Coulomb's law, and it's actually equal to 1 over 4 pi times epsilon naught, and we'll be using this substitution later in the video. The other thing we want to extract from this is information about energies. So what we want to do is look at what half mv squared equals, and this will come in really handy later in the video. So we can also rearrange this to see me times v squared equals k times z e squared over r, right? So if I multiply both sides by half, I'll get half mv squared equals kz e squared divided by 2r. Okay, and half mv squared is the kinetic energy of the electron. So if we want to know what the total net energy of the electron is at a certain energy level. E is equal to the kinetic energy plus the potential energy. So if I want to know what the potential, or the sum is, right, what is the kinetic energy? That's just half MeV squared, which is K times Z E squared divided by 2R, right? And the potential energy is also given by Coulomb's law. And this is another thing that you might have seen in an intro physics class, but I'll just tell you what the equation is here. The equation for potential energy is K times the product of the two charges, so really similar to the Coulombic force, but this is potential. So K times the product of the two charges, and the two charges is the negative E and Z times E. But instead of dividing by R squared, you divide by R. So this is if we sum these two things up, right, we get the total energy of the electron. And this is exactly what we want at the end, right? We want to find a closed equation for what is the energy levels of the electrons in a hydrogen atom or isoelectronic atom or ion to the hydrogen atom. So if we combine these two things, right, this is K times Z E squared divided by 2R minus K times Z E squared divided by R. And this gets us minus K Z E squared divided by 2R. So this equation is exactly what the energy levels in our electron or in our hydrogen atom will be. But what we want to do now is we don't know the radius of the hydrogen atom, this radius that it's orbiting at. So we want to find some sort of equation for the radius. And that's what we're going to do in the next slide when we talk about the quantization of angular momentum. So let's talk about that really fast. I'm going to copy a few things onto the next slide. We have V equals root kz e squared divided by me times r. This was what we found on the last slide. And we also found that the energy level is equal to negative kz e squared divided by 2r. So first let's look at, let's find the radius at which the electron is orbiting, right? This is where we have our idea of quantized angular momentum. And this was what Bohr sort of proposed. And this was how we finally figured out why the energy levels were discrete. And we solved for, theoretically solved for what Rydberg's constant actually was in terms of fundamental constants, and saw that these two the experimental evidence and the theoretical derivation was equivalent. So quantized angular momentum, what does that mean? That basically means that our angular momentum, which is m times v times r, that's our equation for angular momentum, must be equal to n, which is some integer, times h bar. So it's really similar to how Planck said, okay, all the smallest amount of energy delivered by electromagnetic radiation must be equal to h times v, which is some sort of discrete energy packet. Here we're saying that the smallest amount of angular momentum you can have is given by n times a certain integer times h bar, where h bar is some constant, right? So that's sort of the intuition behind it, and we're going to use this to solve for the radius. So what can we do with this, right? We know that n times h bar equals me times v times r, but we also know what v is because it's right there. So we can substitute that v in. So me times r times square root of kz squared divided by me times r. And if we bring the me times r into the square root, we get this is our equation. N times h bar equals me times r kz squared. So this should make sense. This was just simple math. So let's now solve for what the value of r is, right? So we're going to square both sides, and we get n squared h bar squared equals MER KZ E squared, which gives us that R equals N squared H bar squared divided by MEKZ E squared. So it's a little bit messy, but it's just that there's several constants that we have to deal with, but it should basically make intuitive sense, the math that I'm doing. It's not too complicated. The next thing we're going to do is eliminate some of these, substitute some things in for the constants that we have. So H bar, if you remember from the last video, is called the reduced Planck's constant. We talked about this with relation to the Heisenberg uncertainty principle. And it's equal to Planck's constant divided by 2 pi. And K, as I talked about earlier, is equal to 1 divided by 4 pi epsilon naught. So basically what we're just going to do is substitute these two things in. So instead of having K, we have something of epsilon naught. And instead of having H bar, we have something with Planck's constant. And yeah, so let's do that really quickly. And when we do this substitution, what we'll end up getting is that the radius equals N squared epsilon naught H squared divided by pi MEZ E squared. Okay, so this was just making the substitutions and canceling some terms out. Nothing too complicated. So now what are we going to do? Now we have the radii, right? And we also have our formula for the energies. And our radii are dependent on n, which n is our energy level, right? So all we need to do is plug our radii into the energy levels, the energy equation, and now we have a closed equation that gives us the different energies of an electron in a hydrogen or isoelectronic atom. So that is what we're going to do on the next slide. So again, I'm going to copy the two relevant equations over. We have E equals negative KZ E squared over 2R. And we also have that R equals N squared epsilon naught H squared divided by pi MEZ E squared. Okay, so now what we're going to do is plug our expression for the radius into our energy expression. And we should get something like, but first I want to note that in the previous video I talked about how there was a factor of z squared and why there was a factor of z squared. And now you can see mathematically why there's a factor of z squared. There's a factor of z in the energy because the field is amplified by z. But there's also a factor of z in the radius. The radius is divided by z because there's a stronger attraction between the nucleus and the electron. So you can sort of see why they'll end up being a factor of z squared, because you have one factor with the field and you have another factor with the smaller radius. Okay, so now I'm going to continue and do the math really quick. So we're just going to plug this in and algebra it out. It's going to be a little bit messy, but we'll end up with a decently nice final answer. Okay, so now when we simplify this, right, we get negative k z squared pi me e to the fourth divided by 2n squared epsilon naught h squared. But we also talked about how k is just 1 over 4 pi epsilon naught. So let's just substitute that right in. This is 1 over 4 pi epsilon naught. So once we substitute that in, we get negative z squared me e to the fourth divided by 8 epsilon naught squared h squared times 1 over n squared. And I'm just separating this 1 over n squared out so you see that this sort of looks like our energy equation that we talked about in the last video, right? What did we talk about was the energy equation for a single electron, ion, or atom. We said that the energy levels are given by negative z squared h, which is our Planck's constant, times our Rydberg constant, divided by n squared. And now we can sort of match out our terms, right? We can match out our terms and figure out what the Rydberg constant is. So let's do that. We set this equal to negative z squared me e to the fourth divided by 8 epsilon naught squared h squared times 1 over n squared. So we can cancel out our n squareds, we can cancel out our z squareds, and we end up with the formula for Rydberg's constant. Let's cancel out our negatives as well. Rydberg constant equals me e to the fourth divided by 8 epsilon naught squared h cubed. And the reason h is cubed is because we have to divide by our h term on both sides. So we have basically just derived using centripetal force, Coulomb's law, and quantization of angular momentum. We've derived the Rydberg's constant that we were seeing experimentally way before we had a theoretical understanding of it, which is pretty cool, honestly. So I hope you enjoyed this video, and I hope it all made sense. I know I was going a bit fast, but once you rewatch it and just see the math, I think it's not too difficult to understand. The three main concepts that you need are centripetal force, again, Coulomb's law, and quantization of angular momentum. And it's pretty incredible that just from those three simple ideas, you're able to derive Rydberg's constant. Okay, thank you all for watching, and I hope this was informative. I'll see you in the next video.